Have you ever stopped to think about what truly powers your technology? Most people focus on processors, cameras, and batteries. They talk about gigabytes and megapixels and screen refresh rates. But beneath all those specifications, buried in layers of engineering that nobody sees, there's a metal that's been quietly revolutionizing electronics for decades. A metal so critical that without it, the device you're holding right now simply wouldn't function. That metal is silver. And on December 2nd, 2025, Samsung just launched a device that consumes more of it than any smartphone ever created. The Samsung Galaxy Z TriFold went on sale in South Korea on December 12, 2025. Within minutes, every unit sold out. Online pre-orders vanished. Physical retail locations across Seoul reported crowds waiting outside before opening. The device, priced at $2,449 for the base 512GB model, became one of the fastest-selling premium smartphones in Samsung's history. The tech media focused on the obvious innovations: a 10-inch display that folds twice, 3 separate screens connected by 2 precision-engineered hinges, a thickness of just 3.9 millimeters at its thinnest point when unfolded, the Snapdragon 8 Elite processor customized for Samsung, a 5,600 mAh battery, the largest ever installed in a Samsung foldable device, a 200-megapixel main camera, but they completely missed the real story hiding in plain sight. The Galaxy Z TriFold doesn't just represent a new form factor in mobile computing. It represents a fundamental shift in how consumer electronics consume industrial materials. And silver sits at the center of that transformation. Let's start with what we know about conventional smartphones. Research from the University of Plymouth and multiple materials science institutions has documented that a typical smartphone contains approximately 0.34 grams of silver. That's roughly 90 milligrams when you account for manufacturing variations across different models and manufacturers. The silver exists in dozens of critical locations throughout the device: solder joints connecting components to circuit boards, contact pads where connectors meet, printed traces on flexible circuits, antenna elements, conductive adhesives, silver-plated springs in buttons and switches. Every place where electricity must flow with absolute reliability and minimal resistance, engineers choose silver. Why? Because silver is the best electrical conductor in nature. Copper comes close and costs far less. But when you're routing signals at gigahertz frequencies through pathways measured in microns, when you're pushing power through connections that flex and bend thousands of times per day, when failure is not acceptable, you use silver. There is no substitute that matches its combination of conductivity, ductility, and resistance to oxidation. Now consider what happens when you design a device with 3 separate displays connected by 2 folding hinges. The Galaxy Z TriFold has 3 distinct panels. The outer cover display measures 6.5 inches and remains visible when the device is fully closed. Opening the first hinge reveals a central panel. Opening the second hinge exposes the third panel. When fully unfolded, the 3 sections create a seamless 10-inch display surface. Each of those 3 displays requires its own set of electrical connections. Power must flow to 3 separate AMOLED panels. Touch sensor data must route from 3 different touch layers. Display signals must transmit to 3 distinct screen controllers. All of this happens through flex cables that bend every single time you fold or unfold the device. Those flex cables cannot use pure copper. Copper work hardens under repeated flexing and eventually fractures. The standard solution in electronics manufacturing is silver-plated copper conductors. The copper provides mechanical strength. The silver layer ensures low resistance even as the copper fatigues beneath it. Each flex cable contains multiple conductors, and each conductor requires silver plating on both sides to maintain reliable contact through the folding cycle. Samsung claims the Galaxy Z TriFold's hinges are rated for more than 200,000 fold cycles. That's 5 years of folding and unfolding 110 times per day. To achieve that durability, Every electrical contact point in the hinge mechanism uses silver alloy contacts because silver maintains conductivity under mechanical wear that would degrade other metals. Then there's the display technology itself, and this is where the silver content multiplies dramatically. Traditional smartphone displays used indium tin oxide as the transparent conductive layer. ITO has excellent transparency and adequate conductivity when deposited on rigid glass. But ITO is brittle. It cracks when bent. For decades, this limitation prevented the development of truly flexible displays. Engineers tried everything to solve this problem. Graphene films showed promise in research labs, but proved impossible to manufacture consistently at commercial scale. Conducting polymers worked, but degraded over time when exposed to moisture and ultraviolet light. Carbon nanotube networks offered flexibility, but couldn't achieve the conductivity and transparency targets needed for high-resolution displays. The solution that finally worked was silver nanowires. Silver nanowires are metallic filaments with diameters of 20 to 100 nanometers and lengths of 10 to 40 micrometers. They're synthesized through chemical processes that convert silver salts into ultra-thin crystalline wires. When dispersed in solution and coated onto a flexible polymer substrate, they create a transparent conductive mesh that can bend, fold, and flex without breaking. The physics behind this are elegant. When you coat billions of these nanowires onto a surface, they overlap and intersect randomly, creating multiple parallel paths for electrical current. If bending the substrate breaks some of the junctions, current simply flows through alternative pathways. The network is inherently redundant and fault-tolerant. But there's a critical detail that most analyses overlook: the amount of silver required to create these networks. Research published in Advanced Functional Materials and multiple display technology journals indicates that flexible OLED displays require between 70 and 150 milligrams of silver nanowires per square meter of active display area to achieve the target sheet resistance of 85 ohms per square, while maintaining over 90% optical transparency. The Galaxy Z TriFold has a total display area of approximately 0.024 square meters when you combine all three panels and account for the overlap zones at the fold lines. Using the conservative estimate of 70 milligrams per square meter, that's 1.7 milligrams of silver just in the nanowire films, but the actual number is likely higher. The fold zones, where the display bends, require reinforced nanowire networks to prevent circuit disruption at the crease points. Samsung's engineering specifications mention minimized creasing, which suggests additional material layering in those critical areas. Industry sources familiar with foldable display manufacturing estimate that reinforced fold zones can use 2 to 3 times the standard nanowire density. Add another milligram for the reinforced zones. We're now at approximately 3 milligrams of silver in the display nanowire networks alone. The Galaxy Z TriFold isn't just a phone with more screens. It's a device with architectural complexity that scales silver consumption in ways that aren't immediately obvious. Consider the hinge mechanisms. Samsung describes them as armor flex hinges with a dual rail structure using 2 differently sized hinges working in harmony. Each hinge contains dozens of spring-loaded contact pins that must maintain electrical continuity through the folding motion. These pins connect power, ground, display data, touch sensor signals, and control logic between the 3 panels. Every single pin uses a silver alloy contact surface. Gold would work, but costs significantly more and offers no performance advantage. Palladium is cheaper, but oxidizes more readily. Silver provides the optimal balance of conductivity, wear resistance, and cost for high-cycle mechanical contacts. Industry data on flexible circuit contacts suggests each pin uses approximately 0.2 to 0.5 milligrams of silver in the contact plating and spring material. The TriFold has an estimated 60 to 80 contact pins across both hinges. That's 12 to 40 milligrams of silver just in the hinge contact systems. Then there's the 5G antenna array. The Galaxy Z TriFold supports all global 5G bands, including millimeter wave frequencies. Operating at these frequencies requires antenna elements with extremely low resistance because signal attenuation increases dramatically at higher frequencies. Samsung uses silver-based conductive paste for the antenna traces and silver-plated contacts for the antenna feed points. A device with 3 separate panels needs 6 distinct antenna zones to maintain signal strength, regardless of how the phone is folded. Each antenna zone contains multiple elements optimized for different frequency bands. The total silver content in the antenna system likely exceeds 20 milligrams. Now add the standard smartphone silver components that exist regardless of the form factor. Solder joints throughout the motherboard and power distribution network. Contact pads for every connector. The fingerprint sensor contacts. The button mechanisms. Camera module connections. USB-C port contacts. SIM card tray contacts. Wireless charging coil connections. A conventional flagship smartphone contains approximately 300 milligrams of silver in these standard components. The Galaxy Z TriFold, with its additional complexity and triple battery system requiring more power distribution circuitry, likely contains closer to 400 milligrams in these baseline elements. Let's add up the conservative estimates. 3 milligrams in display nanowires, 20 milligrams in hinge contacts, 20 milligrams in antenna systems, 400 milligrams in standard smartphone components. That's 443 milligrams, or approximately 0.44 grams per device. But we're still not done. Manufacturing waste adds another layer. Samsung doesn't publish manufacturing yield data. No consumer electronics company does. But industry analysts and materials scientists can estimate yields based on product complexity and historical data from similar technologies. Early in the production cycle of a new foldable design, yields typically run between 70 and 80%. That means 20 to 30% of devices fail quality control testing and get scrapped or sent for rework. Every failed unit contains a full complement of silver components. If manufacturing yields for the Galaxy Z TriFold are 75%, then for every 4 successful units that ship, 1 unit fails and its materials get recycled or discarded. But silver recovery from electronics waste is notoriously inefficient. The silver in nanowire films is nearly impossible to recover because it's dispersed in thin polymer layers that get shredded during recycling. Silver in tiny contact pins and solder joints gets lost in the separation process. Industry estimates suggest that electronics recycling recovers only 40 to 60% of the silver content. The rest disappears into waste streams or becomes so diffused that recovery is economically unfeasible. So the actual silver consumption per shipped Galaxy Z TriFold unit is significantly higher than the silver content in the finished product. If we account for manufacturing waste and recycling losses, the true silver consumption is closer to 0.6 to 0.7 grams per device that reaches a customer. That's more than double the silver content of a conventional smartphone. And that's before we consider the broader market context. Samsung won't disclose production volumes for the Galaxy Z TriFold. The device launched in South Korea on December 12th, with expanded availability planned for China, Taiwan, Singapore, the United Arab Emirates, and the United States in the first quarter of 2026. Market research firms project that Samsung will manufacture between 1 and 2 million Galaxy Z TriFold units in the first year. That's a small number compared to the 1.24 billion smartphones manufactured globally in 2024. But it's not the current volume that matters, it's the trajectory. The foldable smartphone market shipped approximately 18 to 20 million units in 2024, according to data from IDC and TrendForce. Industry projections suggest 20 to 25 million units in 2025, growing to 30 to 40 million units by 2027 as Apple enters the category and manufacturing costs decline. But now we have a new category emerging: multi-fold devices with 2 hinges instead of 1. The Galaxy Z TriFold is the first mainstream device in this category from a major manufacturer. Huawei launched a second-generation TriFold device called the Mate XT in September 2025 for the Chinese market. Chinese manufacturers including Honor, Xiaomi, Oppo, and Vivo have all demonstrated TriFold prototypes at technology conferences throughout 2024 and 2025. The display industry analysts at DSCC project that multi-fold devices could capture 10 to 15% of the foldable market by 2027. If total foldable shipments reach 35 million units in 2027, that's 3.5 to 5 million multi-fold devices. At 0.7 grams of silver per device, 5 million TriFold smartphones would consume 3.5 metric tons of silver. That's approximately 112,000 troy ounces. Now layer that on top of the regular foldable smartphone market, which continues growing separately. 25 million standard foldables in 2027 at 0.4 grams each equals 10 metric tons of silver. Add the TriFolds, and you're looking at 13.5 metric tons consumed by foldable smartphones alone in 2027. For context, total global silver demand from the entire electronics industry in 2024 was approximately 55 million ounces, or 1,700 metric tons. Foldable smartphones consuming 13.5 tons represents less than 1% of that total. It seems insignificant, except that silver markets are already running structural deficits. Global silver demand exceeded mining supply by more than 100 million ounces in 2023 and 2024, according to the Silver Institute. Industrial applications continue growing. Solar panel manufacturing consumed 165 million ounces in 2024 and is projected to grow 20 to 30% per year through 2030. 5G infrastructure deployment continues globally. Electric vehicle electronics require more silver per vehicle than conventional cars. Every incremental demand source matters when the market is already in deficit, and foldable electronics represents one of the few technology categories where silver consumption per unit is increasing rather than decreasing. For decades, the electronics industry has been systematically reducing precious metal content wherever possible. Computer motherboards that once used heavy gold plating on edge connectors now use thin gold flash over nickel or palladium alloys. Printed circuit boards that used thick silver traces now use copper with selective silver plating only where absolutely necessary. Solder that was once 50% silver now uses tin copper-silver alloys with minimal silver content. This trend drove down per-unit silver consumption in conventional electronics by roughly 30 to 40% over the past 15 years. It's basic economics. When material costs represent a significant portion of manufacturing expenses, engineers find ways to use less material. But foldable displays broke this pattern. Material scientists spent 2 decades trying to find alternatives to silver nanowires for flexible, transparent conductors. They tested hundreds of materials. Graphene remains too expensive and difficult to manufacture consistently. Conducting polymers degrade too quickly. Carbon nanotube networks can't achieve the necessary combination of conductivity and transparency. Metal meshes work, but create visible interference patterns that degrade display quality. Silver nanowires emerged as the only commercially viable solution. And unlike traditional electronics where silver is one option among several, flexible displays fundamentally require silver. There is no viable substitute given current materials science. This creates an unusual market dynamic. Technological advancement, in this case, increases silver consumption rather than reducing it. Every smartphone that transitions from a flat glass screen to a foldable display increases the per-unit silver content by roughly 50%. Every standard foldable that evolves into a TriFold design doubles the silver content again. The industry is moving in the opposite direction of material conservation, driven by consumer demand for larger screens in more portable form factors. Consumer electronics companies don't talk publicly about their materials procurement strategies, but they all operate supply chain teams responsible for securing access to critical materials months or years before production ramps. Samsung manufactures its own displays through Samsung Display, one of the largest OLED panel manufacturers globally. But the company still needs to source silver nanowires from specialty chemical companies. The main suppliers include Cambrios Technologies in the United States, C3 Nano, and multiple Chinese materials manufacturers, including Shenzhen-based firms that dominate the lower-cost segment of the market. These suppliers produce silver nanowires through solution phase synthesis processes. The process starts with silver nitrate or silver acetate dissolved in a reaction medium. Adding reducing agents and controlling temperature and reaction time causes silver atoms to nucleate and grow into nanowire structures. Polymer stabilizers prevent the wires from aggregating. The final product is a dispersion of silver nanowires in water or alcohol that can be coated onto substrates using existing thin-film deposition equipment. Current production costs for high-quality silver nanowires range from $50 to $200 per kilogram, depending on wire diameter, length, distribution, and purity specifications. That's significantly more expensive than bulk silver, which trades at roughly $900 per kilogram. The premium reflects the cost of synthesis, purification, and quality control necessary to produce nanowires with consistent dimensions and minimal defects. This price differential means that silver nanowire demand has a magnified impact on refined silver consumption. If a display manufacturer needs 100 milligrams of silver nanowires, they're effectively consuming approximately 150 milligrams of refined silver, when you account for synthesis losses and production waste. Industry sources suggest that global silver nanowire production capacity reached approximately 100 to 150 metric tons per year by the end of 2024. Most of that capacity serves the display industry, with smaller volumes going to touch sensors, photovoltaic applications, and transparent heating elements. The foldable display ramp is consuming an increasing share of that capacity. As multifold devices enter volume production in 2026 and 2027, nanowire suppliers will need to expand production significantly. That expansion requires corresponding increases in refined silver consumption, ordered months in advance to allow for production scaling and quality validation. This forward demand doesn't show up in current silver consumption statistics, but it represents material that's effectively committed to future production, removed from the available supply, even though it hasn't yet been incorporated into finished goods. Electronic waste recycling has improved dramatically over the past 20 years. Modern e-waste processors can recover gold, silver, copper, and palladium from printed circuit boards with increasing efficiency. Specialized refineries use chemical leaching and electrolytic processes to extract precious metals from shredded electronics. But silver in nanowire form presents a unique challenge. The material is dispersed at the nanoscale through polymer films that are just tens of micrometers thick. When a foldable smartphone reaches end of life and gets processed through typical e-waste recycling, the display gets shredded along with the rest of the device. The shredding process creates tiny fragments of polymer film with silver nanowires embedded throughout. These fragments are too small and too dispersed to separate economically. They end up in the mixed waste stream and get discarded rather than processed for metal recovery. Research from electronic waste management studies indicates that silver recovery rates from flexible displays are below 20%. That means more than 80% of the silver in foldable display nanowire films becomes permanently lost from the supply cycle. Compare that to conventional electronics, where silver in solder joints and contact pads typically achieves 40 to 60% recovery rates. The difference is straightforward. Bulk silver in mechanically separable forms can be concentrated and processed economically. Nanoscale silver dispersed through polymer matrices cannot. As foldable devices become a larger percentage of total smartphone shipments, the proportion of silver entering electronics that never returns to the supply chain increases. This creates a one-way flow from mining to manufacturing to permanent disposal. Unlike investment silver or silver in tableware, which can be melted down and refined repeatedly, silver in modern electronics increasingly becomes unrecoverable once deployed. The Galaxy Z TriFold represents the leading edge of a technology transition that's just beginning. Multi-fold smartphones are currently niche products for early adopters willing to pay premium prices. But the history of consumer electronics shows that today's premium features become tomorrow's mainstream expectations. Touchscreens started in high-end phones and became universal across all price points within 5 years. High-resolution cameras followed the same trajectory. OLED displays, once reserved for flagship models, now appear in mid-range devices. The pattern repeats consistently. Innovation emerges at the top of the market, manufacturing costs decline through volume production, and features trickle down across the entire product lineup. Foldable displays are following this path. The original Samsung Galaxy Fold launched in 2019 at nearly $2,000. The Galaxy Z Fold 7 launched in 2025 at $1,999. Chinese manufacturers now offer foldable devices for under $800. As production volumes increase and yields improve, prices will continue declining until foldable phones reach price parity with conventional flagship smartphones. Industry analysts project this inflection point will occur between 2027 and 2029. At that point, foldable phones transition from differentiated premium products to mainstream offerings across multiple price tiers. Market penetration accelerates rapidly once the price barrier falls. If foldable smartphones reach 10% of global smartphone market share by 2030, that represents approximately 120 to 130 million foldable devices per year based on projected total smartphone volumes. At 0.4 grams of silver per standard foldable, that's 48 metric tons of silver. Add another 5 to 10 million multi-fold devices at 0.7 grams each, and you're looking at total foldable smartphone silver consumption exceeding 50 metric tons per year. 50 metric tons equals approximately 1.6 million troy ounces. That's still less than 1% of total global silver demand. But remember, this figure represents incremental demand on top of all existing industrial applications. Solar panels, electronics, 5G infrastructure, automotive, medical devices, water purification, and dozens of other applications all continue growing simultaneously. Silver mining production has been essentially flat since 2015, fluctuating between 800 and 850 million ounces per year. Mine expansion is slow and expensive. New silver deposits take 7 to 10 years from discovery to production. Existing mines are depleting, and replacement projects aren't coming online fast enough to offset declining output from aging operations. Secondary supply from recycling helps fill the gap, but as we've discussed, silver in modern electronics increasingly enters applications where recovery is technically difficult or economically unfeasible. The available supply of recyclable silver is actually declining as more material gets locked into unrecoverable forms. In this context, even incremental demand growth from foldable electronics matters. The market doesn't need a single massive new application consuming 500 million ounces to create supply pressure. It needs the cumulative effect of 20 smaller applications, each growing 10 to 30% per year, all competing for limited, refined silver supply. Foldable smartphones aren't the only devices transitioning to flexible display technology. Samsung launched the Galaxy Z TriFold in December 2025. But the company also produces foldable tablets, foldable laptops, and has demonstrated rollable display prototypes. Other manufacturers are following similar paths. Lenovo first released the ThinkPad X1 Fold foldable laptop in 2020. The device featured a 13.3-inch OLED display that folded in half. Asus followed with the ZenBook 17 Fold OLED in 2022, using a 17-inch foldable display. HP and Dell both showed foldable laptop concepts at CES 2024. These devices remain niche products with high prices and limited availability, but they demonstrate that the technology is expanding beyond smartphones. Foldable laptops use displays 4 to 8 times larger than smartphone screens. If a 6-inch phone display requires 100 milligrams of silver nanowires, a 17-inch laptop display would require approximately 800 milligrams just for the conductive film layer. Add all the additional silver-bearing components required in a laptop-sized device, and total silver content could easily exceed 1.5 grams per unit. Production volumes remain tiny, probably below 100,000 units globally in 2024. But if foldable laptops follow the same adoption curve as foldable smartphones, shipments could reach 1 to 2 million units per year by 2030. At 1.5 grams per device, that's another 1.5 to 3 metric tons of silver consumption. Then there are tablets. Samsung offers an 8-inch foldable tablet variant available in Korea. Apple is reportedly developing foldable iPad prototypes for potential launch in 2026 or 2027. The tablet form factor may actually benefit more from foldable technology than smartphones do, because users value large screens for content consumption but need portability for travel. A device that unfolds to iPad size but folds to fit in a jacket pocket solves a real usability problem. The automotive industry is also exploring flexible displays for dashboard interfaces, heads-up displays, and entertainment systems. Unlike consumer electronics, where screen size is constrained by device portability, automotive applications can use very large, flexible displays. A curved dashboard display spanning the entire instrument panel might contain 2 to 5 grams of silver in nanowire films alone. Each of these categories remains small in absolute volume today, but they're all growing, and they all use the same underlying material: silver nanowires embedded in flexible substrates, because no other material provides the necessary combination of conductivity, transparency, and mechanical durability. Technology adoption follows predictable patterns, but the pace can surprise even experienced analysts. Touchscreen smartphones went from 0 to 1 billion units per year in less than a decade. OLED displays penetrated the smartphone market faster than anyone projected in the early 2010s. The Galaxy Z TriFold launched in December 2025. By December 2035, 10 years from now, foldable devices may represent 30 to 40% of smartphone shipments. Multifold devices with 2 or more hinges could account for half of those foldables. Total silver consumption from foldable electronics across smartphones, tablets, laptops, and automotive applications could exceed 150 to 200 metric tons per year within a decade. 200 metric tons represents approximately 6.4 million troy ounces. To put that in perspective, the entire jewelry and silverware industry consumes roughly 180 million ounces per year. Photovoltaic solar panels consumed 165 million ounces in 2024. The 5G infrastructure build-out uses approximately 20 million ounces annually. Foldable electronics would still be a relatively small slice of total silver demand at 6 million ounces per year, but it would rank among the top 10 industrial applications globally. And critically, it would be one of the fastest-growing applications, expanding at 20 to 30% annually, while many traditional applications grow at single-digit rates or even decline. This matters because silver markets, like most commodity markets, operate on the marginal unit. When supply and demand are relatively balanced, even small changes in either direction can create significant price movements. The silver market has been in deficit for several consecutive years. Above-ground inventories are declining. Exchange stocks are at multi-year lows. Investment demand from both institutions and retail buyers has been increasing. Adding several million ounces of incremental industrial demand from a new application category that didn't exist 5 years ago puts additional pressure on an already tight market. And unlike cyclical demand that rises and falls with economic conditions, foldable electronics demand is structural. Once manufacturers design products around this technology, the silver consumption becomes embedded in production processes and continues regardless of broader economic cycles. The Samsung Galaxy Z TriFold isn't just an impressive piece of engineering, It's a window into how technology evolution can fundamentally alter industrial material consumption patterns in ways that aren't obvious until you examine the details. Every year, the electronics industry finds new ways to do more with less. Processors become more efficient. Batteries store more energy per gram. Displays get brighter while consuming less power. Material science advances allow engineers to use cheaper alternatives to expensive metals in most applications. But flexible displays reversed this trend. They require more silver per square centimeter of screen area than conventional displays. As devices get more complex with multiple folds, silver content per unit increases rather than decreases. The technology advances, but it advances in a direction that increases material intensity. This creates an unusual situation where consumer demand for innovation directly drives increased consumption of a finite industrial material. Every person who buys a foldable smartphone because they want a larger screen and a smaller form factor is unknowingly contributing to incremental demand for silver that didn't exist when they bought conventional smartphones. The Galaxy Z TriFold sold out in minutes when it launched in South Korea. Customers paid $2,400 for access to cutting-edge technology. They received a device that represents the pinnacle of current smartphone engineering. What they didn't know is that hidden inside their premium device, invisible in layers of circuit boards and display films and hinge mechanisms, there's approximately 0.7 of a gram of silver, working silently to make every fold, every touch, every signal transmission function exactly as expected. 0.7 of a gram sounds insignificant, but multiply that by millions of devices. Multiply those millions by annual growth rates exceeding 20%. Project that growth forward 5 to 10 years as the technology matures and costs decline and adoption accelerates. Suddenly, you're looking at tens of millions of troy ounces of incremental silver demand entering the market, from an application that barely existed in 2020. The silver market is enormous, with annual mine production exceeding 800 million ounces. But it's also fragile, running persistent deficits as industrial demand grows faster than mining supply. In fragile systems, small perturbations can have outsized effects. A few million ounces of unexpected demand can tip a barely balanced market into significant shortage. The Galaxy Z TriFold launched 3 days ago. Initial production volumes are small. Most of the world hasn't heard of it yet. But Samsung isn't the only manufacturer pursuing this technology. Every major smartphone maker is developing foldable and multi-fold devices. The technology is spreading from phones to tablets to laptops to automotive displays. The adoption curve is just beginning its upward trajectory. 5 years from now, when foldable devices have become common enough that nobody thinks they're particularly special anymore, when prices have dropped enough that mid-range models compete with conventional phones, when multi-fold designs are standard in flagship lineups across all major brands, somebody in the silver industry is going to look at demand data and wonder where all these extra millions of ounces of consumption came from. They'll trace it back to dozens of sources: solar panel growth, electric vehicle adoption, 5G expansion. And buried in that list, they'll find a line item for foldable displays that's consuming quantities of silver that would have seemed impossibly large back in 2025 when the Galaxy Z TriFold first launched. The device in your pocket, or on your desk, or folded in your bag right now, contains materials that required mining operations on multiple continents, chemical synthesis in specialized facilities, precision manufacturing processes more complex than most people can imagine, and global logistics networks shipping components across oceans and borders. Most of those materials are common, but some are scarce. And some are becoming scarcer as technology evolves in ways that increase rather than decrease consumption. Silver is one of those materials, and folding your phone in half just became a lot more materially expensive than anybody realized. Subscribe to stay informed about the hidden material trends reshaping technology and the invisible connections between consumer products and industrial commodities. Leave a comment below sharing your thoughts on how everyday devices silently consume critical materials that most people never think about.